Good afternoon. Welcome to Java today and tomorrow. So this talk is a bit about Java today, look at some features that you can use right now. It's mainly an attempt to peer into the future at what's coming down the road. So hopefully you'll find this interesting. A fair amount of this is demos. I will probably make at least one mistake. If you see me make a mistake and I'm stumbling, feel free to shout out. Sometimes that's actually really helpful. So, but before we get into these features, both present and future, let's talk just a little bit about what drives Java forward. For 23 years, it's really been about pursuing two big goals. One goal is developer productivity. Java is about helping developers build and maintain large and reliable programs. It's not about one-off script. It's not about just hacking around. It's about building things for the long haul, being able to maintain them. Java is also about program performance. And program performance, of course, is measured in many different ways. There's time, startup time, latency, and throughput. There's space, static and dynamic. There's scalability from iPhones to Big Iron. So lots of different ways to measure that. For 23 years, we've pursued these two big goals in the face of constantly evolving factors, constantly evolving programming paradigms, such as mixed functional and object-oriented programming or data-oriented programming, evolving application areas, big data, and machine learning, evolving deployment styles, such as to the cloud and to app stores, and of course, evolving hardware, terabyte memories, deeper memory hierarchies, vector and SIMD instruction sets on GPUs, and faster and deeper and more numerous processor pipelines. Okay, so let's take a look at how we're pursuing those two goals in light of all these factors in some of the major active projects in the OpenJDK community. First, we have Project Amber. Brian Getz is driving this. It's all about right-sizing language ceremony. Project Loom, continuations and fibers for the Java virtual machine, at last. Ron Pressler is leading this one. Panama is about improving the interface between Java and foreign functions and foreign data. That's being led by Maurizio Ciamadamore. And finally, Valhalla, value types and specialized generics, which is being led sort of by both John Rose and Brian Getz. So let's start with Amber. Right-sizing language ceremony. What does that mean? Well, it's a maybe a more polite way of saying reduce the boilerplate. I'm so tired of it. Java is well known for its boilerplate. And we have been on a mission over time, as Venkat was explaining this morning, to reduce the amount of boilerplate. It's especially painful in the modern era of data-oriented microservices. So our solution is not to just try to compress everything down as much as we can. I mean, we could turn Java into APL, and it would be nice and compact, right? But it wouldn't be readable. So we're not going to do that. Our solution is a series of language features delivered over time, which we can now do every 6 months on the rapid cadence, that let you express more clearly what you mean. And if you can express more clearly what you mean, our experience has been that generally all the boilerplate just takes care of itself. So let's look at some Amber features. The first one we'll look at is local variable type inference. This is in Java 10. I've often heard people say that, oh, type inference, that's like you find that in those fancy languages like Haskell and whatever. Java doesn't have type inference. No, nothing could be further from the truth. Java has had type inference for a long time. For example, in Java 5, we introduced type inference along with generics. Generics could have been designed like this. So every time you invoked a method with a generic type, you would have to give that parameter. But, well, that would be stupid. To quote Venkat, you want the compiler to work for you, not you to work for the compiler. So you can write this, the obvious thing, the thing that we've now been writing for over a decade. In Java 7, we introduced the diamond operator. So we look at code like this. It's like, OK, new array list of string. I type string once. And over on the left-hand side, I have to type list of string again. But yeah, come on. The compiler knows it's a string. So you can just put the diamonds in there, the diamond in there, and just type string once. In Java 8, when we introduced lambda expressions, lambda parameter types could have been designed like this. So when you write a lambda, you always have to write the types of its parameters. But no, the compiler knows what it is, so let's just leverage that knowledge, and you can just type S. I mean, you can type the whole type if you really want to, and sometimes that's actually useful documentation, but you don't have to. And often it's a burden. In 10, we've introduced local variable type inference. You look at a statement like this. Buffered reader equals new buffered reader, new filed reader. I mean, this is code you could have written, in JDK 10 in 1996. And it still works, of course. Java's all about compatibility, but it's tedious. I mean, all these readers, buffered this, buffered that. Why do I have to not just write buffered reader twice? Why do I have to read it twice? So in 10, local variable type inference, you can just type var. So this is not turning Java into JavaScript. This is not dynamic typing. This is still static typing. It's strongly checked. It's just less keyboard typing along the way. This is especially useful in typical kinds of sequences of statements that are all related, that are doing something that's all tightly coupled. And typing this stuff on the left is just tedious. New URL equals new URL connection. URL connection, new scanner, It's just much nicer if you can read it this way. Now, it does mean that you should probably be maybe a little more careful in choosing your variable names. One-character variable names, when you don't have to put the type on the left-hand side, can be even more confusing. But there you go. There actually is a surprising amount of subtlety in using these things well. Let's see. So this is in Java 10. It's defined in JEP 286. You can use it today. Of course, since it's in 10, it's also in 11. It'll be there in the future. To learn more about using var with style, you can go to Stuart Marks's talk in room 5, Thursday at 9:30 a.m. All right, let's move on to another Amber feature, raw string literals. How many people use regular expressions? How many people like regular expressions? Well, yeah, okay, now you have two problems, I know. Here's something you could write today. So this dot matches, double quote backslash w backslash, all these backslashes, because you're inside the quoted string and you have to backslash the backslashes. You really only need one backslash for the regular expression, of course. Okay, and of course, in a more complicated regular expression, this gets really hard to read, especially if your regular expression is trying to match something that contains backslashes. So what raw string literals allow you to do is write this. Now, that's probably a little hard to see. Those are backticks on either end. Let me magnify it for you. So matches backtick, /w, one /w, and then another backtick. So you open with a backtick, you close with a backtick. And with the syntax, you can write whatever content you want. It is not interpreted. \u escapes are not interpreted. Backslashes are not interpreted. The only interpretation that we do, and this is a small concession to portability, is a carriage return new line is replaced by just one new line. I mean, sorry, Windows. Somebody had to win. It would make sense for code compiled on one platform to have different new line conventions in its raw strings than code compiled on another platform. So we had to normalize to something. So there you go. Okay, so those are the backticks. Now this is useful not just for regular expressions. Again, suppose you're dealing with Windows, where file name paths, for whatever reason, I've never understood it, use backslashes instead of forward slashes, as Dennis and Ken intended. Anyway, here we are. You've got file paths with backslashes in them, and typing stuff like this is just tedious. So you can type a raw string literal, and oh, it looks like it actually should look. That's nice. It goes further. Suppose you need to spew out a little bit of HTML text. Sure, you could go use some proper XML or HTML API to do this, but you just want to get the job done. So you do this. You've got this multi-line string. You have to double quote each line and then append them, which the compiler will see, and it'll concatenate everything. And okay, no, this is just boring. So with the raw string literal, you can actually cross over lines. After all, what would be the point of all that line normalization if we couldn't actually use it? So here, we type that literal, right there in the text, surrounded by these backticks, and you're done. Now, to make that more readable in the multi-line case, you can actually use multiple backticks. You start with one or more backticks, and you end with the same number of backticks. That way, if you really want to, you can have backticks in the middle, and it works. You just can't have the number of backticks that you used to start or end the quote. Now, if you think about this carefully, you'll see that there will be some white space in the resulting string literal that's due to the way that this code is indented. It's indented so that it looks good as Java source code, but we probably don't want that indentation. We probably want the HTML opening element to be right at the margin. So we've added an align method to strings. So you can invoke a line, it will figure out where the logical left margin should be and remove that many spaces from the beginning of every line. If you're using tabs, sorry, there's no heuristic in the universe that will understand what the right thing is, and we just don't process that. There are a number of other useful things added to string that help use raw string literals. So raw string literals are in Java 12, JDK 12 already. You can download the builds from jdk.java.net. They're a preview feature. So they're not enabled by default. If you write some code like this in a source file or crank up JShell, you'll get an error message saying, "Huh?" But if you enable preview features, which you do on the command line by typing --enable -preview, then it will be enabled. You'll get a little warning to remind you that it's enabled, and you can go on and play with it. And please do play with it and tell us what you think. Okay, that's raw string literals. Now let's move further on to switch expressions. Suppose you've got an enum, day of the week, Monday, Tuesday, Wednesday, and so forth. And suppose further you want to compute the number of days in the week. Now, if there's a slicker way to do this, right? You just get you just do toString on the day of the week object and count its length. But we're going to do this for the sake of the example. We're going to switch on the day, and we're going to say, well, case Monday, case Friday, case Sunday, num letters equals 6. Break and go down to the bottom, and then eventually, we go through all of this, and num letters will be assigned something, or we will have thrown an unexpected day exception. Why do we have to have that default clause? Because, well, that's the sensible thing to do when you're dealing with a switch and maybe you're not quite sure what day is. Now, all kinds of stuff can go wrong here, right? You can forget to assign to num letters. You can forget a break and have an accidental fall through. It can just get ugly in a whole bunch of ways. Now, all you're really doing here is computing an expression. So let's write it that way. Into num letters equals switch on day. Case Monday, Friday, Sunday, return 6. Case Tuesday, it's 7. Thursday, Saturday, it's 8. Wednesday, it's 9. And there's no default needed. The compiler can analyze this sufficiently well. Since enum classes are final, the compiler can tell that you've covered all the cases. There's no need to put a default in here, so you don't need to do that. So that's pretty cool. Switch expressions are also in Java 12 and JDK 12 as a preview feature. So again, please, if you'd like, download the build from jdk.java.net and try it out. All right, let's move on to things that are not yet in any early access build. We've all written code like this. Okay, I need to model some geometrical thing. I need points, so I've got a point class, final double X, constructor, accessors. Pretty straightforward. But wait a minute, I forgot a whole bunch of stuff, didn't I? Didn't I? Yes. Did I forget stuff? Right. Equals hash code and toString, our old friends. Got to have those. And so you type out the usual stuff, or as Venkat would say, your IDE can vomit it out for you, and then you just hopefully it's correct. Kind of like with a switch statement, it's easy to cut corners. It's easy to introduce bugs, and if you've got IDE generated code, that can help with writing, but not with reading. After this code has evolved for a while, you've still got to read it in order to maintain it. The encapsulation you get by having this in a class isn't actually necessary. Look, I mean, we're exposing all of its fields through the accessors. We don't need this strong encapsulation. There's a movie quote in there somewhere. What we really need is a way to say this class it's just a transparent container for data. Records let you do just that. You say record point double x double y, boom, you're done. And you get the equivalent of all the code that's now faded away. We've replaced all that POJO stuff with just one line because sometimes data is just data. I don't need all this fancy object-oriented stuff. Now, if you need to, you can customize a record. So I've got my point record. I can override its hash code if I prefer a different hash code method. I can define additional methods. Maybe I want a norm method that returns the mathematical norm of the point. I can customize the constructors to check some preconditions. What I can't do is add an instance field. So the compiler will not allow you to do this because that would violate the invariant that a record is a transparent holder for data. You cannot add new state to a record because then it wouldn't be a transparent holder for data, and a bunch of the mechanisms we want to build on top of it would not work. All right, so records are there. You can find an sorry, question? Sure, why not?
Well, is this immutable or not?
Records are immutable. If that doesn't work for you, you can write a class. There's always the fallback. You need something that a record doesn't have, write a class. Good question, thank you. All right, so that's records. There are some prototype implementations of this, but it's not in any early access build yet. Let's move on to another cool thing. We've all written code like this, right? Well, I've certainly written a lot of it. You've got some object, it's of some type. You probably have an idea of which types it is, but you don't know exactly which, so you do an instance of test. If it's an integer, then you have to cast it to an integer, and then you can do this format string that we're trying to create. Otherwise, check if it's a double, you check if it's a point, so on and so forth. This is just tedious, so let's make it better. We do that with pattern matching. So pattern matching lets you do both a type test, and actually more generally a precondition test, on an object or value, and if that test works, it will bind one or more variables for you. So when here we see ob instance of integer I, if ob is an integer, then it will cast it to an integer for you, bind it to I, and then in the scope of that if branch, you can use I, and it refers to an integer, not an object, so you don't have to cast it. And likewise for all the other cases. So that's a pretty nice improvement. We can go further. Pattern matching plays well. It's all designed to play well with switch expressions. This looks awfully a lot like it could be a switch expression, right? And indeed, once all these features are done, they will work together in this manner. You can just switch, and the switch cases are determined by these patterns. You return the value that you want to return. We even have deconstructors, so you can say, in your case, point of xy, it will deconstruct the point object, bind its two values to x and y. You can use x and y in the body of that case statement. And of course, here we do need a default because it came in as an object. We really don't know much about it. Okay, so that's a selection of features being worked on in Project Amber. If you want to know more, you can go to Brian Getz's talk on Friday, 11:40 a.m. in room 8, where he'll go into a bunch of this in more detail. So let's move on to Loom, continuations and fibers for the Java virtual machine. At this point, I will attempt to switch to the other machine. If we're lucky, it looks almost the same. Huh. Well, that's entertaining. I'm not sure why that stuff at the bottom is there, but it is. All right, continuations and fibers for the Java virtual machine. Let me remember where I am. Oh yes, it's Devoxx, isn't it? Yep. Okay. So we all know about threads, right? We've had threads in Java from the very beginning. At the time, it was a fairly novel thing. but threads are now pretty commonplace. Let me go over to a command line. Yeah, that glitch, that's a glitch in the matrix down there. Nothing I can do about it, sorry. Demo, loom. Do this little demo. What am I running? Java version build I did just a couple days ago. Well, no, just about a month ago. Of the Loom prototype. I didn't update to the latest one because I asked Ron, should I update to the latest one? And he said, no, it's much less stable. Use the one you used last month, it's fine. So let's go into JShell and take a look around. So we've got threads, we've had them forever. I can type stuff like this, var t equals new thread. Whoop. Println, thank you. So we do that. D is a thread, I can start it. It runs, it does its thing. Threads have actually gotten to be kind of heavyweight objects, right? You can do all this stuff with threads. They carry a lot of baggage from the past. They have thread groups. They have priorities that actually don't mean much on most platforms. Every one of them corresponds to an operating system thread, which is usually expensive to create. It's expensive to switch from one operating system thread to another. That leads people to write non-blocking I/O code, for which, of course, there's a very fine non-blocking I/O API in Java. And you can make stuff go really fast that way, but it's notoriously difficult to get non-blocking code right. So in the end, servers wind up being underutilized because, well, writing sequential code is just easier. There's other baggage in here too, like a context class loader. Why did we ever decide to associate a class loader with a thread? The decisions of the past. So threads are kind of heavyweight. In Loom, we will have fibers. So let me make a fiber. And actually make a fiber much like you make a thread. Fiber. And I get a fiber back. Now, in its two-string output, it says no carrier thread. So fibers are just insanely lightweight threads. They're not associated with an actual operating system thread until they need to be. And that decision is made by the Java runtime system rather than by the operating system. So it has much more intimate knowledge of what's going on in the application. And switching can happen without calling into the operating system. In general, it's much faster, but it works a lot like a thread. We don't say start on fibers, we say schedule. Schedule that fiber, it says hello. And then when it's done, you still got the fiber, and now it has no carrier thread again. Fibers are simpler than threads. If I look at the methods on fiber, not much there, is there? I mean, like half of these methods are inherited from Java Lang object. But it's got a schedule method. It's got cancellation. You can wait for one. You can ask if it's alive. Fibers, it turns out, work well with completable futures. So I can say completable. Whoop. If I can type here, future CF equals fiber schedule. And I've got a completable future. Call cf.get, it'll schedule the fiber, it'll run it, and return the result as a result of the completable future. So if you have an existing code that uses completable futures, you can pop fibers up right in very easily. So fibers are also designed to make it fairly straightforward to migrate from an existing library or framework that uses threads to fibers. So we're going to do that right now here live with the Jetty web server. Wish me luck. Okay, I'm going to, let's drop into my favorite IDE, namely Emacs. Demo Loom, REST demo, source, main, Java, Loom, sleep service. We're going to use this example of a little REST service that's using Java RS. We've got a path for it. We've got some annotations on this method called sleep. so that the JaxRS runtime can find everything and bind it. The sleep method it's just going to sleep. We're going to pretend it's actually doing work, but for the sake of the demo, all it's going to do is sleep for a little while, 100 milliseconds by default. Pretend it's doing some work, so we can see what goes on when it's under some concurrent load. Okay, so first let's run Jetty, and we'll use threads by default. Since I'm a lazy developer, I packaged all this up into a makefile. So this goes off, it runs Jetty. We're using the Vegeta HTTP load generator. It warms up for 4 seconds, and then it runs for 8 seconds, which is long enough to get interesting results. It makes a plot, so let's go look at that plot. I think it's here. All right. So this is the response time measurements for the Jetty web server under load using threads. As you can see, it starts out kind of okay, but then it progressively gets worse, and it gets very spiky and unpredictable. I mean, we've got pauses here of pushing 2 seconds, way up over here. Even further down, if we zoom in, you see these spikes because all this work is going on in the operating system and everything else. All right, so let's go back and we will run it with threads. Now the change to do this in Jetty is actually fairly simple. I think this is in the main class. So one of the cool things about Jetty is that you configure it by writing some Java code. You don't write a pile of XML or anything ugly like that. You just write Java code. It's got a nice API for setting up the server. And you can, among other things, tell it what thread pool to use. And so what we do is we just kind of fake it out. Since fibers work almost exactly like threads, we provided a new thread pool, and the key thing we do is we override this execute method. Rather than creating a thread and starting it, we create a fiber for the runnable command for the web server, and we schedule it right away. So the Jetty code actually has no idea that it's running on fibers instead of threads. There we go. Okay, so now I will make fibers, and we'll do the same test, but with Jetty running on fibers. Warm up for 4 seconds, run for 8. Hopefully it doesn't crash. Sometimes it does. Oops, connection refused. This is not going to be good. Let's look at the data. Oops, yeah. And let's see. Oh, yes, HSRP ID. We know what's in there, don't we? A fatal error has been detected by the Java runtime environment. If you'd like to submit a bug report, ... Okay, so what we do is we just run it again. Ron, thank you for the advice. I did not want a less stable build than this one. Cross your fingers, everybody. Looking good. Okay, it's not taking too long. Usually takes a really long time if it crashes. But it's taking, oh no, it's taking a long time. Oh, no, maybe that worked. Let's look at the graph. Yes. Now, it's actually kind of hard to see. That's the whole idea, believe it or not. So let's zoom in on this graph. Let's zoom in some more. And you can see very quickly, so the orange line is the response time with fibers. It never exceeds 130 milliseconds. It settles down into a pattern where almost every response is just over 100 milliseconds, which is what we like to see, pretty quickly, and it stays there. There's the occasional spike. It's probably garbage collection or something. But wow, that's a lot better than threads, isn't it? Okay, so that's Jetty running on fibers. Fibers are not just about avoiding non-blocking I/O. I mean, that's certainly a big payoff. They also open the door to many other new techniques, such as channels and data flow and actor models that are really efficient. And all the cool things, all these are implementable on top of the JDK in libraries. They don't have to be in the platform itself. Now, I did mention continuations. Continuations are really cool. If you're an old Lisp hacker, you know what continuations are. They're great. They're extremely powerful. They are the low-level JVM mechanism upon which fibers are built. They are useful for other things, such as generators and stuff like that. But in general, this bringing fibers and continuations to Java, it's another example of what Java has done, quite successfully for a long time now, which is look at other languages and platforms, learn from their experiences, identify key abstractions that Java doesn't have, and then figure out how to fit them into Java in a way that makes them look like they've always been there. Okay. Let's switch up. Right. If you want to learn more about Loom, Alan Bateman, who's working closely with Ron Pressler on this, will speak about Loom tomorrow at 4:40 p.m. in room 9. Today. Oh, today is Wednesday, isn't it? I'm sorry. It's like, all I knew for about a week was the keynote was this morning. Question, sir?
If they're similar in what they do they inherit a common interface?
Yes, an excellent and very deep question. If they're similar, then they do inherit a common interface, or does fiber extend thread, or does thread extend fiber? I suggest you come to Alan's talk, and he will probably get into the conundrum that we face there. We don't know what the best answer is. It certainly should not be the case that fiber extends thread. The case that I personally think is the right direction to go in is fibers are things unto themselves. Let's keep them lightweight, let's keep them slim and trim and really, really fast, and then provide an easy way to migrate from threads to fibers, or fibers to threads if you really have to. But yeah, Alan will go into this in much more detail, I'm sure. Okay, so that's some on Loom. Panama, foreign functions and foreign data. The motivation for Panama is that invoking native code, interacting with native data that's outside the Java heap is slow and cumbersome. JNI, the Java native interface that we've had just about forever, is too painful and it's slow to boot. Little trivia fact from history, JNI was designed to be slow. You catch me with a suitable beverage in my hand, and I'll explain why that was. To use JNI, you have to write C code. You compile it into a native library. You have to load the library. You've got this SO or DLL flying around. Panama is designed to be a new Java to foreign to Java bridge. It includes a Java API that models C data types. There's an extraction tool. We're building this on top of Clang that transforms C and C++ header files into Java interfaces. So your code can use the API almost as if it were a Java API. And its third main component is there's a runtime binding mechanism that synthesizes implementations of those interfaces that were generated by the extractor at runtime. So you don't need to carry around an SO or a DLL. It's all handled at runtime. This allows you to write, what 20 years ago someone would have said, oh, you can't do that. You can write platform and architecture specific Java code. But, well, that's a good thing because it's Java code and it's not C. All right, so let's look at some Panama examples. All right, let's cd into demo Panama. Got the right build. Yep. Panama, freshly built, November 10th. There we go. So we're going to do one of the canonical demos. Hello World, right? The canonical demo from way back when. If you're doing something like Panama, one of the canonical demos is get PID, get the process ID. Do the most trivial Unix system call that you can, and find out what your process ID is. So here's the man page for get PID. What does it tell you? Invoke get PID. It doesn't take any arguments, and it returns a PID-T, which is really just an int. And you can find all the right definitions in systypes.h and unistandard.h. So what we're going to do is we're going to run this extraction tool called jextract against user include unistandard.h, and we're going to put the output here. And it goes off and parses all those header files and everything else that it includes, and we get some stuff back. And it turns out we get quite a lot of stuff, but near the top there you can see unistandard.class. So let's run Java P on that. And lo and behold, oh, that actually looks kind of familiar, doesn't it? There are a bunch of Unix system calls with some things translated. Ints become ints. Other richer things become uses of the foreign memory API in Java. And if we go further down, we can find what we're looking for. Here's getPid. Abstract, in getPid, this is in an interface. This is not an abstract class. It's just that Java P prints out abstract because it's an interface, because whatever. All right. So we've got that. We've got the unistandard class. We can now take a look at some Java code, which I happen to have here. Getpid.java, we import the foreign API, the foreign memory API, and method handles because we need that to get started. We go down. We invoke this bind method in the Panama runtime that takes a method handle so it can get the context of your code right here. And you pass in unistandard.class, so you're asking, synthesize me an implementation of that extracted interface so that I can invoke the getPid method. And then I just invoke the getPid method. It returns an int, I print it. And for reference sake, since of course we can get the process ID in Java, we'll just do that here to check it. And if this works correctly, this code should print out the same value twice, right? Okay, so let's run it. And I'm using the slick source code launcher feature, so I don't need to compile this first. Boom, there's the process ID. No C code, no .so file, no DLL or anything like that. But I invoked a Unix system call. So not only can we get things back, we can actually operate, use the C API to operate on native data. We can pass interesting structures in. And we can even use those structures to get sophisticated values back, things that are more complex than an int. Let's look at another canonical example, clock get time, modern version of get time of day. So clock get time takes a clock ID, which is just a constant, and then it takes this struct time spec, which is it's a trivial structure, but it is a struct. It's got a couple of fields, which are defined down here. It's got a seconds field and a nanoseconds field. We want to invoke this. What do? Well, we do essentially what we did before, but there's a little more work to be done. So let me clean things up here. We'll clean up and we'll run jextract. I packaged this up because it needs a bunch more arguments that I didn't want to type out in real time. And we get some classes in here, the demo package. Whoops. So there's a bunch of stuff here. The interesting stuff is struct time spec. So the extractor created, among other things, classes that hold the constants from the time spec thing and the interface for which implementation will be synthesized. So let's go back into Emacs and we can look at clockGetTime.java. So again, using the same APIs, we import relatively more stuff. We start out here by declaring, using the C memory model API to create a new native scope. So a new scope in which we will manipulate some memory that can be passed to and from native or foreign code. We allocate a struct using some of the information that we got from the extractor. Then we invoke clockGetTime. We tell it which clock we want, the real-time clock, and we give it a pointer to this time spec struct. And then when we're done, we can print the results. And again, for reference, we'll have it print system current time millis, and these values should be similar, right? So let's make clock. Whoops. Make run clock. There we go. We got more precision out of the system call on the first line, but as you can see, it's essentially the same value that we got from current time millis. So there's no fakeage going on here. So with Panama, there's still quite a ways to go here But the fundamentals are working. One of the hardest things is what to do with all the stuff that you find in C and C++ headers files. It's extraordinarily complex, and there's structure there, but you have to interpret so much to figure out what the structure is. It's not totally clear we'll be able, always to synthesize beautiful Java APIs for stuff that came out of a big pile of C and C++ header files. So we're working on that. Don't know how far we're going to be able to push it. But if you want to know more, you can go to Maurizio's talk Wednesday, that's today, 3:10 p.m. in room 10. So right after this talk, if you're really excited about Panama, you can go learn more from Maurizio. Panama early access builds are available on jdk.java.net if you really want to live on the bleeding edge. All right. Let's move on from Panama to Valhalla, value types and specialized generics. The big motivation for Valhalla is that today's processors are vastly different from those of 1995 when Java was first designed. The cost of a cache miss alone has increased by factors of 200 to 1,000, depending on the class of processor you're talking about. Chasing all of the pointers that are inherent in Java data structures is really, really expensive. Why are there so many pointers? Well, there are so many pointers because every object in Java has identity. Every object on Java is a thing you can type double equals on. Every object on, you can synchronize on any Java object. That was convenient, but in retrospect, maybe it wasn't the best design choice. But there it is. We can't break that. So what are we going to do? And stuff like this is just especially painful for big data and machine learning applications. So to address this problem, we think the missing abstraction is value types. That's the ability to declare pure data aggregators that don't have identity or don't necessarily have identity. That, okay, maybe for compatibility you can synchronize on them, but it's more expensive to do that. So if that's a problem for you, don't do that. But we still want to consider them as defined by Java classes. But since they're values, we can do slick things like allocate them in registers. We can flatten data structures. In general, John Rose has this great motto for the project called "Codes like a class, works like an int." Right? An interesting juxtaposition. It almost sounds oxymoronic. All right, let's look at a little example, which I just happen to have. Let's look. Okay, so we're going to do, first make sure we got the right thing here. Yep, freshly built. We're going to do matrix multiplication. Now, matrix multiplication is not something that you see done very often in Java because, well, if you do it the obvious way, it's clunky and slow, as we shall see. Source main Java Valhalla. So I've got complex numbers. Actually, before I do that, so that I don't mislead you, main Java. Okay, package Valhalla, public class complex. Looks a lot like the point thing I showed earlier, right? It's got two fields, real and imaginary, constructor, accessor, and operations to do point add and point multiplication and so forth. Or sorry, complex add and complex multiplication. And then we'll do a multiply, just using the standard order of n or cubic algorithm. So we get the length of our arrays. We do the obvious loops. We compute the dot product of each element, and boom, we've got a resulting matrix. There's a bunch of annotations in here and the setup methods because I'm doing the right thing here and using Alexei Shiplev's very fine Java microbenchmark harness to run the measurements. Okay, let's run this. As we could run it today, not doing anything fancy, no value types here, just a lot of boxed complex objects. So I'm going to run Maven because that's how JMH works. I'll do a warm-up, some warm-up iterations. This is all being handled by JMH, one of the really cool things about it. Yeah, it's taken a while there. Iteration measurement, iteration 1, we'll do 3 iterations and measure them along the way. Our matrix glitch is still there. Right away you can see, well, this is why we don't do matrix multiplication in Java. If this is a 500 by 500 matrix, it's taking almost 4 seconds to do a multiplication. And along the way, we're allocating almost 4 gigabytes. Ooh, wow. That's pretty sad. Okay, let's look at that in the log files easier. Here's the log. So each operation took about 4 seconds. Let me mark that. Allocation rate, about 4 gigabytes per multiply. And another interesting figure is the instructions per cycle. So the processor in this laptop, it's an Intel Core i7 Skylake, it's actually capable of retiring 4 instructions per clock cycle. And here it's poking along, retiring barely more than 1. So it's spending a lot of time waiting for the memory system to chase those pointers and get the complex data so it can do the multiply. All right, so we'll keep that around. We can look at it later. I'm going to go to complex here. I'm going to do one thing. I'm going to type value class complex. And then I'll pop back out. And I'll run the same exact test. Run Maven again, because that's how JMH works. Warm-up iteration. Ooh, wow, that's already a lot faster. Right? Before we were pushing 4 seconds, now we're 200 some. Do some iterations. Iteration 1, iteration 2, iteration 3. Back to the log file. We'll keep these figures on top. And we'll go down to the bottom. So the bottom is with value classes, and the top is with boxed complexes. Whoops. Each operation took 293 milliseconds. So to do a quick calculation, 3, 8, 9, 5, 9, 293. That's a factor of 13 speed up. Not bad. Instructions per cycle. We retired almost 3 instructions per cycle during those tests instead of just barely 1. And the allocation rate per operation was 3 megabytes. Mainly just for the matrix result. We didn't have to do allocation along the way to allocate any complex objects because they're all values, everything was flattened. And the matrix itself is almost entirely flattened rather than being separate complex objects in memory. Okay, so that's Valhalla. It's pretty slick. It's coming along. Valhalla is some really deep cuts in both the language and especially in the Java virtual machine. If you want to hear more about this, you can come to Brian's talk. Again, his futures talk. He'll be talking about both Amber and Valhalla on Friday, 11:40 a.m. in this room. That's a quick look at 4 projects. They're just starting to bear fruit. It's a really exciting time. We see code working. We can see the future that we've been talking about for a long time in a much clearer way now, and it looks pretty exciting, which is nice. If you want to learn more, not only the sessions I referred to, but we're doing an Ask the Architect session on Friday, 9:30 in this room, where I and my colleagues will attempt to answer any and all questions. Just don't make them personal, like Venkat. We will probably not answer those. Don't believe a word I've said. Thank you very much.